PEC to its friends in dilute atomic gases. I actually finished what I was going to say about that, but just a quick review of what we did towards the end of the class. We found that if we had a three-dimensional harmonic well, holding an ideal gas, so it's confined in a trap in kind of a spherical cloud, where the well has a circular frequency omega 0, that when the temperature is below some non-zero critical temperature, the Einstein temperature, the fraction of the atoms which are in excited orbitals is temperature divided by Einstein temperature cubed. For the Einstein temperature, we found a number from doing an integral. It was 0.94. The level spacing associated with the frequency of the trap, and then a factor depending on the total number of atoms, n to the 1/3. We said that at a temperature tau, the size of this thermal cloud, our thermal which we estimated just by saying the typical potential energy of an atom is comparable to the temperature. It would be about temperature divided by m omega naught squared to the 1/2. The potential energy going like m omega naught squared r squared, setting that comparable to tau, that's what we get. If we consider the interatomic spacing in the gas, that's the volume per particle to the 1/3 power, we said that goes like h bar squared over m tau to the 1/2, temperature divided by Einstein temperature. H bar squared over m tau, that's something that has the dimensions of length. I called it the thermal wavelength. Now it's the typical de Broglie wavelength of a particle with mass m, whose kinetic energy is about tau. And so, as we lower the temperature and reach the Einstein temperature, condensation kicks in when tau is equal to tau e, when the typical distance between the atoms in the trap is comparable to the de Broglie wavelength. We also compared that to the width of the ground state wave function in the trap. It's a harmonic oscillator. The wave function is a Gaussian. The width of that Gaussian, delta x in the ground state, is h bar over m omega naught. And actually that just comes from saying, or to estimate it in order of magnitude, the potential energy associated with deviation from the bottom of the trap, delta x, is comparable to the energy level spacing h bar omega. So if we compare that to the size of the cloud, we can write it as the size of the cloud, the radius of the cloud, a factor going like n to the minus 1/6, and then there's a square root of tau Einstein over tau. So when the condensate kicks in, as we're lowering the temperature, when tau is equal to tau e, if n is very large, the ground state orbital has a width which is quite narrow compared to the size of the cloud. We have a big fraction for tau below tau e of all the atoms in the ground state wave function. We're treating it as an ideal gas, so they all have the same profile. If we try to detect a particle in the ground state orbital, of course the square of this Gaussian gives the probability distribution. So the density of atoms as a function of position, and it's really a three-dimensional distribution, but if we take a slice through it, there's a broad thermal distribution of atoms in the trap, and then a much narrower peak associated with the ground orbital. And as the temperature cools through the Einstein temperature, this peak shoots up above the thermal distribution. And by imaging the gas, by taking a flash picture of it with a laser, for example, one can see that peak and verify that the condensate has formed. So for the typical type of trap that people have used in this experiment, one can estimate this Einstein temperature. We have to know h bar omega naught. It's omega naught in the kilohertz range typically. The experiments that Ketterle described in his article, n was something like 10 to the 7, so the n to the 1/3 is a bit more than a factor of 100, and the corresponding Einstein temperature, if we put it in degrees, is about a microdegree, something like 10 to the minus 6 degrees Kelvin. Well, that's why we speak of ultra-cold atomic gases. It's really kind of the coldest stuff you can make. Okay, so a lot of h-bars in the lecture last time. Rest of today, h-bar free. Nothing quantum. It's all classical. In fact, it's probably stuff you've heard before, but that's okay because it's very beautiful. It was done in the 19th century, which is not to disparage it. Something that's lasted that long must be good. The theory of heat engines. Okay. So what we want to consider is a system which can be brought into contact with either one of two reservoirs, a hot reservoir and a cold reservoir. There's a hot reservoir, we'll call that RH. It has a temperature tau h. And cold reservoir, I'll call that RL. It has a temperature tau L. So high temperature H, low temperature L. We can bring the system into contact with either one at our choice. Operating a heat engine means using controlled flow of heat from the hot reservoir to the cold reservoir while producing useful work. So we can bring the system into contact with the warm reservoir, have some heat flow into the system, withdraw some heat from that reservoir, expel some heat to the cold reservoir, and then we can use the difference between the heat that we extract and the heat we expel to produce work. That's how a heat engine operates. Well, the principle is used in many different ways in technology for generating electricity with, say, steam turbines, internal combustion engines, and many other things. Now, the first thing that we need to get straight is we're going to make heavy use of conservation of energy, the first law of thermodynamics. which says that the change in internal energy for the system can be written as the difference between work done and heat flow. That should be plus, I guess. Actually, so I'm writing it this way, so then dW is positive if work is done on the system, which increases the internal energy. dQ is positive if heat flows into the system, which increases the internal energy. I'm going to do something I didn't do before, which is to put a little tail through the D. And that's to remind us of something important, which is we can think of U as a so-called state function. That means that if you know the state of the system, you know its internal energy. Okay? W and Q are not state functions. So if you like making, as usual, imperfect use of the English language, U is something that a system has. We can say S has energy, but S does work. Knowing what the state of the system is, we can say how much energy it has, but we can't say how much work it has. Now, the reason that's important is that in the theory of heat engines, we're going to consider systems undergoing what I'll call a closed cycle. That means we'll start out in some initial configuration of the system, it'll undergo a series of changes, and come back to the initial configuration. So in particular, if I consider what that looks like in the pressure-volume plane, perhaps I start out at some particular value of the pressure and the volume, and then the system expands for a while and goes to some final value, and then later, I'm going to draw it in a way which will look kind of crazy, but maybe it'll make it a little easier graphically. The reason it looks crazy is as the volume is increasing, the pressure is going up, which isn't what happens under the types of change that we usually consider. But just to illustrate the point, the pressure varies as the volume changes in some way. And we know that the work that's done, dW, can be written as PdV. This is the work done by the system as it expands. Okay? And so if I want to integrate that to find the work done during this change, it's just the area under this curve. But then I want to change the system back from this configuration to the initial one. And let's say it changes back like that, with the pressure varying as a function of the volume in the way I've indicated. And so this is now going to describe work done on the system, negative work done by the system, because the system is being compressed, and the total work done is the area under this curve. If I want to know what the net work is, I take the work that the system does during the first half of the process, subtract away the work that is done on it in the second half of the process. So overall, it changes like that, and then back like that. Okay? And the net work done is the total area enclosed. That's the difference between the area under the upper curve, the work done by the system while it's expanding, and the area under the lower curve. Minus that is the work done by the system while it compresses, or in other words, the work done on the system while it's being compressed. So this is the net work done, this area. And I can write it this way: an integral with a circle, meaning it's an integral over some closed cycle of pdv. That's equal to the network. If you like, you can write it as the integral over this closed cycle of dw. Well, the reason I put the slash through the d is that if w were really a state function, like u is, if I considered under a closed cycle the integral of du, fundamental theorem of the calculus says that's u final minus u initial as we go around the closed cycle. But we come back to the initial configuration at the end. So the final internal energy is the same thing as the initial internal energy. Over a closed cycle, the integral of du is 0. But the integral of d slash w is not. It's really the integral of p dv. P is a state function, and so is v. But the area enclosed in the p dv curve, the network, is not 0. We can't think of that as the change between the initial and final configuration of the system's work, because it comes back to the same configuration it was in initially. Okay? So we don't get confused about that. I put a slash through the d. And we'll still get confused about it. It won't be my fault. And similarly with q. So I can write, as we know, the heat flow in or out as tau d sigma. Okay, so sigma is a state function for the system, so is tau. If we add some heat, the system's entropy increases slightly. But it's possible over a closed cycle for the net amount of heat added to be non-zero. Q itself is not a state function. So integral over a closed cycle of d slash q does not have to be 0. Just like the work. Well, in fact, the two things are related, right? Because of the first law. If I integrate du over a closed cycle, that's certainly 0, because u is a state function, but I can write it as the integral of d slash w plus the integral of d slash q. And they can be separately non-zero, but they have to be equal and opposite. So the integral d slash w, which is the integral of p dv over the closed cycle, can be the work done in a closed cycle, and that will be equal, because u is a state function, to minus integral d slash q equals minus integral of tau d sigma over the closed cycle. So there's a balance. Conservation of energy says the net work done in a closed cycle I guess be careful with the minus sign. So I've defined this as net work done on system. As I said, du was pdv with the plus sign. I may regret that, but anyway. So du increases when the system... Oh shit, did I get that wrong? du increases when the system expands. So that's the work done by the system. Isn't it? And the work done by the system, so I define dq to be the heat flow This doesn't look right, does it? Work done. Oh, I see. I wasn't consistent. So if I want, so this this means it's the work done on the system, and therefore I should put a minus sign here, right? Does that look right? Then when the system expands, the work done on the system is negative. When it's compressed, the work done on the system is positive. So then I would put this here, and then get rid of this, and this, and this. So the net work done by the system is the net heat flow into the system. Those minus signs will kill you. Yeah.
Is there a minus sign there? On the other board there.
Yeah. I guess so, huh? Network done by system is minus PdV, because when the system is being compressed, okay, hold on. I guess I should decide whether this is the convention I'm going to be using from now on. Well, it's almost guaranteed I'm going to change my convention, so let's not worry about it. So anyway, so let's suppose I stick with this. Okay, so dW, when it's positive, the internal energy increases. That means it's the work done on the system. And dQ is positive. That means du is positive, so that's the heat flow into the system. And so if I want dW to be the work done on the system, I have to say minus PdV, so that when the system is being compressed, dV is negative and the work done on the system is positive. So this is fine. This is also right. And then this does have a minus sign, right? But sorry, now I'm saying that the integral dW is the work done on the system. That's why I put the minus sign here. So the net work done on the system is the how about I do this and that, and then I can say the net work done by the system is the net heat flow into the system. How's that? Because that's right. The work done by the system is the difference between the heat it takes in and the heat it expels. Or something with different minus signs, which makes sense. You decide. Okay. Sorry?
Erase the middle board.
Oh, did I? Right, thank you. I'm reluctant to, because there probably are wrong things there. Okay. All right, so we want to talk about thermodynamics, because the origin of thermodynamics lies in the recognition that there are fundamental limits on how much of the heat added to a system can be converted to useful work. So what are limitations on converting heat to work? So I'm going to consider what I'll call an ideal heat engine. So the picture, again, I'll draw it again, but slightly differently than before. We have a reservoir at a high temperature, tau h. A heat engine extracts heat from the hot reservoir. It expels heat to a low temperature reservoir, a temperature TL. TL is less than TH. And it produces some work, W, taking advantage of net heat flow from the high temperature reservoir to the low temperature reservoir. So the three ingredients in the ideal heat engine are, first of all, that there are two reservoirs. So S can be brought into contact with either of two reservoirs with temperatures tau h and tau L, where tau h is the larger of the two. Second, we're going to consider the system undergoing a closed cycle. That means S returns at the end to the state it was in initially. S returns to its initial state. So because it's a closed cycle, we can imagine repeating the cycle many times. And I want to consider a closed cycle for another reason as well. I want to keep track of the energy balance between the net heat added to the system and the work done by the system, and I don't want to have to take into account work done by changing the state of the system. So the system is going to wind up in the same state as it was in initially. And the third thing, which is the key to the meaning of the word ideal, is that the system operates reversibly. So that means, in principle, we can run the whole thing backwards instead of forwards in time. It also means, as in our earlier use of the word reversible, when we talked about the second law, that there is no net change in the entropy of the whole universe. So the entropy that the system gains when it draws heat from the higher temperature reservoir matches the entropy that it expels when it expels heat to the lower temperature reservoir. So I'll say entropy expelled. Obviously the system's entropy is the same at the end as it was at the beginning, because entropy is a state function and it goes back to its initial state. But some entropy is withdrawn from the higher temperature reservoir. That's what I mean by entropy withdrawn. And that has to match the entropy expelled. To the lower temperature reservoir in order for the overall change in system plus reservoirs to be reversible, to leave the entropy unchanged. So the heat that we withdraw from the high temperature reservoir is given by dq with that funny tail on it equals tau d sigma, or in other words, the heat withdrawn, I'll call that QH for Q flowing into the system at the high temperature tau H, is the temperature, tau H, times the change in the entropy of the system when the heat flows in. I'll call that delta sigma. And minus that is the change in the entropy of the hot reservoir. The heat that's expelled which I'll call Q sub L, I'm going to write it so that it's positive. It's the temperature at the lower temperature reservoir times the entropy delta sigma. So delta sigma here I'm defining to be positive. It's the amount by which the system's entropy increases when it extracts heat or withdraws heat, and QL means the positive amount of heat that exits the system and flows to the lower temperature reservoir. It's the same value of delta sigma, but different amounts of heat because the temperatures are different. And the important thing is, this is where the reversibility came in, it's the same delta sigma for both the heat withdrawn and the heat expelled. So the entropy lost by the high temperature reservoir is equal to the entropy gained by the low temperature reservoir. Okay. Now, the system undergoes a closed cycle. Oh, as I've already said, the integral du, or the change in the internal energy, is equal to 0. The system goes back to its initial configuration at the end of the cycle and has the same internal energy as it did initially. And that means, from the second law, that there's a match between the first law, from the first law, conservation of energy, that there's a match between work done and net heat extracted. So work done by the system, W, is heat taken in from the high temperature reservoir minus heat expelled. But I can write that in terms of delta sigma using the expressions for QH and QL. Is tau H minus tau L delta sigma, where tau H delta sigma is QH, tau L delta sigma is QL. And if I factor out tau H times delta sigma, in other words QH, that's 1 minus tau L over tau H times QH. Now we may define the efficiency of our cycle, of our heat engine, as the fraction of the heat that it takes in that it's able to convert to useful work. I'll call it eta. It's the work done in the cycle, the net work done in the cycle, divided by the heat that the system takes in from the hot reservoir, W over QH. So if I divide both sides of the equation above by QH, That means I can write the efficiency as 1 minus tau L over tau H. I might prefer to write it as tau H minus tau L over tau H. And I'll call that eta sub c. It's the efficiency that's attained by an ideal heat engine. And the C is for Carnot. We call it the Carnot efficiency. Now, this is the efficiency of the ideal, that is reversible, heat engine. Now, in practice, sometimes it comes as a surprise to physics students. In practice, things are not always perfect, and so we can't attain the ideal efficiency for various reasons. There's friction, there's some uncontrolled heat flow from the high to low temperature reservoirs, there's some irreversible expansion, and so on. But the efficiency of the ideal engine places a limit on the best efficiency possible. And in general, the process won't be perfectly reversible. We will have a net change in the entropy of the world, which is positive, and that will mean efficiency strictly less than Carnot efficiency. Notice that the Carnot efficiency, the best possible, is strictly less than 1. So not all of the heat withdrawn can be converted to work unless the lower temperature reservoir has 0 temperature. So if tau L is not 0, then the efficiency is strictly less than 1. Unavoidably, there is some waste heat. Some of the heat that gets withdrawn from the system, if the system that gets withdrawn from the high temperature reservoir by the system, if the system undergoes a closed cycle, the system has to expel some heat if the lower temperature reservoir is not at exactly 0 temperature. And so the efficiency is less than 1, even in the ideal case. Well, I emphasize that everything is reversible, by which I mean it can be reversed. So suppose we consider heat flow in the opposite direction. A system that takes in heat from the lower temperature reservoir and expels heat at the higher temperature. So same picture, but with the arrows going in the other direction. Here's the system. Heat flows in. QL coming from the low temperature reservoir. It gets expelled. QH at temperature tau H. And now, instead of work being done, work is done on the system W. Okay? Now what do we call that? The system is doing work. Heat is being withdrawn from a low temperature reservoir. It's being expelled to a high temperature reservoir. What is that? It's a refrigerator. If I reverse a heat engine, it becomes a refrigerator. And we can, as a measure of the performance of a refrigerator, use a different notion of efficiency. Because now what we want to do is we want to keep the beer cold, so we want to withdraw as much heat as we can from the refrigerator. So our figure of merit is how much heat can we withdraw from the cold place per unit of work that we do, so we don't have to pay a high electric bill. Well, the best possible refrigerator, again, operates reversibly without any change of entropy. So we know what the best possible refrigerator efficiency is. It's that is achieved by a reversible refrigerator undergoing a closed cycle. So we can repeat the cycle over and over again. If it's a closed cycle, no change in the internal energy. The work that the system does is the difference between the heat expelled at high temperature and the heat taken in at a low temperature. So, again, there's going to be some entropy change in each reservoir, and they're going to be equal and opposite because overall the entropy doesn't change. It's a reversible process. So, for the same delta sigma, I can write QH as tau H delta sigma, and QL is tau L delta sigma. So if I factor out this time QL, I can write that as tau H over tau L minus 1 times QL, or QL is tau L delta sigma. So when I call it gamma, my measure of efficiency for refrigeration, the amount of heat withdrawn per unit of work done, in the ideal case, is 1 over tau H over tau L minus 1. So I can write that as multiplying through by tau L over tau H minus tau L, which I'll call gamma C, again C for Carnot, the ideal efficiency of a refrigerator in the case where it operates reversibly. Now, unlike eta, the efficiency of a heat engine, gamma can be large compared to 1. If the difference between, well, I mean, if it is, if the difference between the high and low temperatures is small compared to the value of the low temperature on the Kelvin scale, the absolute temperature scale. So I'll say if tau H slightly above. Okay? So that's because in order to pull a lot of heat from the refrigerator, we don't have to do very much work because we're going to expel the heat at only a slightly higher temperature. In fact, we could expel the heat if the temperatures were the same. We could take heat from the low temperature reservoir and put it in the high temperature reservoir without doing any work at all because they're at the same temperature, right? So as the temperatures approach one another, the ideal efficiency of a refrigerator gets large. So suppose I want to heat my house, although today I don't, but sometimes I do. So I have a furnace, and it burns fuel. So there's a chimney. And so actually the way I heat my house is I burn some fuel, and the amount of heat that warms up my house, Q, is equal to what I'll call W, which is the energy released by burning the fuel. my case, it's a natural gas furnace. But I have a friend who's better educated in thermodynamics than I am, I guess. Well, he has an air conditioner, but unlike me, he uses his air conditioner to air condition the outdoors. Okay? So you think he's kind of a silly guy, but so his house is nice and toasty warm. It's at a temperature tau H, and outdoors there's a reservoir at temperature tau L, and he is doing work to pump heat from his house, the high temperature reservoir, to the low temperature reservoir. So he's air conditioning the outside. So, if I call QH the amount of heat that I produce in my house, I could say the amount of heat that I get per unit of energy consumed by burning fuel is 1, because I happen to have a perfectly insulated house, except when the dog goes in and out the dog door, but that's not that often. Okay, but what about my friend? Well, he's refrigerating the outdoors, so the work that he does in a cycle is the difference between the heat that he extracts from the low temperature reservoir and what he deposits in the high temperature reservoir inside his house. So in his case, the amount of heat for energy that he consumes is actually tau H over tau H minus tau L. So it's like the Carnot efficiency, except we have a different criterion here. Instead of asking how efficiently are we making the thing that we're refrigerating cold, we're asking how efficiently are we heating up the warm reservoir, because I want to heat up the house. I don't care about how cold it is outdoors, really. So that's the ratio of tau H to the difference tau H minus tau L. And that can be much greater than 1. So my friend is actually much smarter than I am. He runs his air conditioner backwards. We call that a heat pump. Okay. And so, you see, I'm being kind of stupid because I'm heating my house as though it were absolute zero outside. Okay, but it's not, especially not today. But even when it's cold, the temperature outside isn't absolute zero. So I'm not taking advantage of a resource. There's a reservoir at non-zero temperature outside. And my friend is exploiting that resource. He wants to move heat inside, but he only has to do an amount of work, which is the difference between the amount of heat that he moves into the house and the amount of heat he withdraws from outdoors. So a heat pump from the point of view of ideal thermodynamic efficiency makes a lot more sense than direct heating. But while there are various engineering details which we don't usually worry about as physicists, which make the heat pump not necessarily the preferred choice. Heat pumps are kind of expensive. Although some modern houses have air conditioning systems which can be run in reverse and act as heat pumps. Part of the reason it's not necessarily economically the best option is that it's cheaper to burn natural gas like I do than to use up electricity like my friend does, running his air conditioner backwards. Okay, so what I want to do now is talk about a particular example of the system. And conceptually this doesn't add much other than just maybe make contact with discussions of heat engines you've seen earlier and give us yet another opportunity to use what we know about the classical ideal gas for about the 5th time. So let us use a classical ideal gas as the working fluid in a Carnot cycle and examine stroke by stroke what's happening. That's called the Carnot cycle. So I have a piston. And there's some gas inside. It's an ideal classical gas. The piston can move in and out. We can bring the working fluid, the ideal gas, into contact with either one of two reservoirs at tau h or tau l. So I'm going to consider a closed cycle which has 4 steps. In the context of heat engines, they're usually called strokes. Well, I'll call them strokes. It will be an ideal heat engine, a reversible heat engine with 4 strokes. There will be 2 isothermal strokes. One at temperature tau h, one at tau l. At the higher temperature reservoir, we're going to want to let the gas, expand or contract? At higher temperature, we want to withdraw heat from the high temperature reservoir. So we want to let it expand, right? So that isothermally, heat will come in from the reservoir, the gas will expand and do some work. When it's in contact with the high temperature reservoir, I want to make it a closed cycle, so I'm going to have to compress it again, but I'll do that in contact with the low temperature reservoir to expel some heat to the low temperature reservoir. And there will be 2 isentropic strokes. So during those steps, we'll imagine the system is isolated from either reservoir, but we have to include steps which change the temperature of the system. We wanted to exchange heat between the high temperature reservoir and the low temperature reservoir. We want to do it irreversibly. When we bring it into contact with the high temperature reservoir, the temperature of the system has to match the temperature of the reservoir, or else it wouldn't be irreversible. It wouldn't be reversible. There'd be some irreversible heat flow. And then I have to bring the temperature down to tau L before I let it come into contact with the low temperature reservoir. So the change in the temperature, that's going to take place during the isentropic strokes when the system is isolated. So it's simplest to think about this in the sigma tau plane. So I'll start down here. The first stage is going to be isothermal expansion. System is in contact with the high temperature reservoir. So here the temperature is tau h. Over here it's tau L. And in the first step, the system expands. That means entropy is coming from the reservoir to the system. The system's entropy is increasing. So that is isothermal expansion. Isothermal, temperature staying the same. In the second stroke, I got to bring the system down to temperature tau L. And I'm going to do that by allowing it to continue to expand, but now no longer in contact with the reservoir. It's got to expand so it continues to do work that will lower its internal energy, bring down its temperature until we reach tau L. So this is isentropic, constant entropy expansion. That's the second stroke. Now we've got it cooled down to tau L. We let it come into contact with the low temperature reservoir. But now we have to get the entropy out. So now we're going to compress isothermally so that entropy flows from system to lower temperature reservoir. So that's step 3, which is isothermal compression. Now I got to bring it back to the original temperature tau H because I got to close the cycle. So I do that by continuing to compress, but now with the system insulated, not in contact with the reservoir. So that will be isentropic compression. That's the fourth step. And it completes the cycle. We can repeat it again and again. Since it is a closed cycle, no change in the internal energy. Therefore, the work done matches the heat flow. So I can write the work done as the integral over the closed cycle of tau d sigma. And that is just the area enclosed by this rectangle. Okay, I guess maybe you should turn your head 90 degrees, and then we are doing a d sigma integral. So I consider the area, under this curve, but then I subtract away the area under that curve to find the net heat flow. The result is the area enclosed by the rectangle. And that is the difference between the entropy taken in here, tau H, times the change in the entropy, minus the entropy expelled, the heat flow taken in during the isothermal, I guess that's right. The heat taken in during the isothermal expansion at high temperature minus the heat expelled during the isothermal compression at low temperature. The same change in the entropy in both cases. Well, actually, I didn't make very much use of my assertion that it was a classical ideal gas. But now I will, just to compute explicitly the work done and the net heat flow during one cycle. So now it's going to be an ideal gas with PV equals n tau. And I'll draw it in the pressure volume plane instead of the entropy temperature plane. So the first stroke, we start up out here, is isothermal compression. We let the volume increase. The pressure is falling off like 1 over V. Then we remove the system from contact with the high temperature reservoir, let it continue to expand. Now, isentropically, the volume falls off more steeply during that stroke, which is isentropic expansion. So all this time the system's been doing work. Now we have to bring it back to its original configuration so we can repeat the cycle. It's cooled enough to reach the temperature of the low temperature reservoir at this point. At that temperature, we can isothermally compress. That's the third step. And then we remove contact with the low temperature reservoir and continue compressing isentropically.
Is step 1 isothermal?
Yes, step 1 corresponds to this step. We're in contact with the high temperature reservoir and its expansion. Good point. Thank you. Or, as I like to think of it, negative compression. Isentropic compression is the last thing. And that's the closed cycle. The work done is the difference between the work done by the system during the first two steps, which is the area under this curve, but then I subtract away the area under this curve, the work we do on the system. When we complete the cycle of the net work is the area enclosed. All right, so how much work is done during the first stroke by the system? Well, dW is equal to PdV. I integrate that from the initial volume to the final volume during the expansion. And now I use the ideal gas law, which tells me that the pressure is falling off. Temperature is fixed because it's isothermal. Pressure is falling off like 1 over V. So I'm integrating from the initial to final volume, dV over V. The integral is natural log of V. So it's n tau times the log of the ratio of final volume to initial volume. During the second stroke, unlike the first, the internal energy is changing because the temperature is changing, and there's no heat flow during this stroke. The internal energy for an ideal gas, 3/2 n tau, and so the work done is the change in the internal energy. That'll be 3/2 n times the initial temperature minus the final temperature. During that isentropic expansion, the temperature is going down. In fact, the initial temperature is the temperature at the warmer reservoir. And so we begin the isentropic expansion when the system is in contact with the high temperature reservoir, and we let it expand until it is at the same temperature as the low temperature reservoir, temperature tau L. Now remember, if you want to know how the pressure is related to the volume, during isentropic expansion, well, we have to remember what the entropy is, because isentropic means entropy constant. For our ideal gas, I'm assuming it's monatomic, by the way. So it's the log of quantum concentration divided by concentration plus 5/2 times n. The temperature is changing, the volume is changing, n is not changing. So I can say, since the quantum concentration is proportional to temperature to the 3/2, that what is being held constant is the log of tau to the 3/2 volume divided by n, since 1 over concentration is volume divided by n. And actually n is a constant. So if that's a constant, it means that V times tau to the 3/2 is a constant during isentropic expansion. And since we can use the ideal gas law, which says that temperature is proportional to PV, since n is a constant, I can equivalently say, writing temperature as PV, that V to the 5/2, pressure to the 3/2, is equal to a constant during the isentropic expansion. Or in other words, that the pressure, taking the 2/3 power, is going like volume to the minus 5/3. Okay. So in other words, we can say that the final pressure at the end of the isentropic expansion divided by the initial pressure is the ratio of volume, V initial to V final to the 5/3. And since volume is proportional to temperature to the minus 3/2, right, because tau to the 3/2 times volume is equal to a constant when the entropy is held fixed. I can say that the ratio of final volume to initial volume is initial temperature divided by final temperature to the 3/2. Now, the work that's done during the isentropic compression and the isentropic expansion, they exactly cancel one another, because in both cases it's just determined by the change of temperature, and the difference between the initial and final temperature is the same for both the isentropic compression and the isentropic expansion. So the net work done is the difference between the work done during the isothermal expansion and the isothermal compression. So isentropic compression, well, I'll say absolute value, so I don't have to worry about getting the minus signs right. is equal to the work done during the isentropic expansion. One's negative, the other is positive, so they completely cancel out. The net work, then, is the difference between the work done during stroke 1 and stroke 3. So W net for the cycle, isothermal compression, work done by the system, minus a work done on the system during isothermal compression. Work done by the system during isothermal expansion, minus work done on the system during isothermal compression. This is the work done. In one case, the temperature is tau H. In the other case, it's tau L. So I can write that as N times the difference between tau H and tau L of the log of the volume difference, BF over VI. Now, I can also write the ratio of the initial to final volume in terms of the temperature, because I know that during the I can use the relationship between volume and temperature, that the volume goes like temperature, where is that anyway? Temperature to the minus 3/2. So I can write that as 3/2 N tau H minus tau L times the log of the ratio of temperatures, tau H and tau L. Yeah.
That's the isothermal, not isotropic.
You mean why am I using this? Yeah, so let's see.
Yeah, but that's applying for the higher isotropic.
Yeah, right.
And I think the amount of work being done does depend on VF over VI.
Let's see. So, well, at least we can say this, right? We can say that the what's the change in the entropy during the isothermal strokes, which we need to know what the heat flow is. And since the entropy is given by this, when it's isothermal, the temperature and N are fixed, so the entropy is going like the log of the volume. Right, so entropy goes like n log v when tau is constant. So the change in the entropy during the isothermal change in volume is n times the log of the ratio of the initial to final volume. And the change in the entropy, of course, is going to be the same in both isothermal strokes because we're considering a reversible process. So the ratio of final to initial volume is the same in both strokes. And the heat taken in by the high temperature reservoir is just n times tau h times the log of the volume ratio. And we computed the work by integrating the PDV. So the net work, which I guess I wrote down over here, the useful work produced when we take in an amount of heat QH is tau h minus tau L times the log of the volume ratio divided by n tau h, the log the volume over the initial, which of course is tau h minus tau L over tau h, as we knew it would be because we're considering an ideal heat engine that operates reversibly. And what we learned in addition by using the ideal gas law is the amount of heat and the amount of work per cycle in terms of the ratio to the initial to final volume during the isothermal expansion and compression. So back in the 19th century, it was popular to state the second law of thermodynamics this way. It is not possible to extract heat, say heat Q, from a reservoir and convert it to work without producing waste heat. Unless there's a zero temperature reservoir. With tau lower equals 0. Which certainly follows from our statement about Carnot efficiency being less than 1 if tau L is positive. Now it's kind of an interesting observation that it follows just from that statement that all heat engines or refrigerators that operate between reservoirs with given temperatures, tau h and tau L, which are reversible, have to have the same efficiency. So there's some universal efficiency, which we've seen follows just from the requirement that the entropy stays the same, the Carnot efficiency. But we can also infer that as a corollary to the second law stated this way, if by reversible we just mean something that can run backwards. So let me show you that argument. It's kind of cute. Well, corollary to the second law is that all reversible heat engines operating between reservoirs at temperatures tau H and tau L have the same efficiency. And reversible just means it's possible to run it backwards. Okay, to see that this is true, suppose it's not, we'll argue by contradiction. The idea is that if you have a lower efficiency heat engine and it's reversible, then it provides a higher efficiency refrigerator. So suppose there's a heat engine, I'll call it heat engine 1. It takes in heat QH from the high temperature reservoir, it expels QL, and it produces work, which is the difference, QH minus QL. Okay, but suppose there's another heat engine which operates reversibly. Call it heat engine 2. And it's less efficient, so it takes in a little bit less than QH. It produces an amount of work which is a little bit less than heat engine 1, while producing the same amount of waste heat QL. So for the same amount of waste heat, it's doing a little bit less useful work. It's a less efficient heat engine. But it's reversible, so let's imagine running it in reverse. I'm going to use it in series with heat engine 1, and I'm going to use it now as a refrigerator to pump the waste heat produced by heat engine 1 back to the high temperature reservoir. So QL comes in to heat engine now refrigerator 2. The amount of work done by refrigerator 2 is W minus delta W. It's less efficient, I should have said, if delta W is positive. And it expels to the high temperature reservoir QH minus delta W. Okay? So operating as a refrigerator, 2 is better because it's removing the amount of heat QL from the low temperature reservoir, and it's doing work W minus delta W. If I use 1 as a refrigerator, in order to remove QL, it would have to do W. Okay? So if it's a worse heat engine and it's reversible, we reverse it, it's a better refrigerator. When we combine 1 and 2 together in this way, 1 as a heat engine and 2 as a refrigerator that pumps the waste heat of the heat engine back to the high temperature reservoir, 1 and 2 together have not expelled any heat to the low temperature reservoir, because all the heat expelled by 1 has been pumped back by 2. But the net amount of work produced by 1 and 2 is actually delta W, because the amount of work we got out of the heat engine was more than the amount of work we had to do running the refrigerator. So have produced positive work delta W greater than 0 are without waste heat. But that violates the second law. So if we're going to avoid this quandary, all reversible heat engines operating between reservoirs at the same temperatures have to have the same efficiency, since a less efficient heat engine would be a more efficient refrigerator. Okay. Of course, the amazing thing about all this stuff, or most of it, is that it was understood by Sadie. Question.
Isn't it wasting the heat Q sub H minus delta W?
Well, it's not, because it is expelling no heat to the low temperature reservoir. If we combine the two together, it is using an amount of heat from the high temperature reservoir delta W, because it used QH here, and then it pumped back QH minus delta W. So altogether it has taken delta W from the high temperature reservoir, produced work delta W without any waste.
Got it.
Yeah, Carnot was an engineer. In 1824 he wrote his only scientific paper ever, and he died not too many years later, about 8 years later, and received no recognition for his work. But even though at the time, this was 1824, the law of conservation of energy hadn't been formulated, the mechanical equivalent of heat had not been discovered by Joule, he understood that in order to operate a heat engine, you had to have controlled flow of heat from high temperature to low temperature. He understood that there was an ideal efficiency. He understood that it was necessary to have waste heat, and it was really an amazing achievement, but it wasn't really recognized and didn't become widely known until after his death, when Kelvin discovered Carnot's work and let the world know about it. Okay.